Welcome to today's webinar. The topic today is wind load determination for rooftop equipment. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today, and I will answer your questions during the webinar. My colleague Clemens Gutmann will be the presenter today. He's responsible, for example, for the add-on form finding and the program Wind. And yeah, he works also in the customer support team. So I say something how you can ask questions. At first I switch off my webcam. Just press the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that should be for the moment all from my side. I hand over to Clemens. Clemens, you can start.
Thank you, Andreas, for the introductory words. I also want to welcome you to today's webinar. The topic of today's webinar will be one of the application areas of Wind3, carrying out variance studies. So whenever you are in a decision-making process in the preliminary design phase, for example, where you have to decide about something geometrical that also affects the wind load on your building, you can use Wind3 for that. So in our case, or in my case, the example I brought today, I want to look at a roof ventilation system and more specifically determine whether the height of the attic has an influence on my structure, on this ventilation system, and if there's an effect, is it significant or not, and how does the change of the attic's height influence the results. Of course, we are also going to look at the required mesh settings and the analysis settings, and finally take a look at the results. So without further ado, let's jump into the program. So I already modeled this ventilation system. Here it's a basic, a very simple geometry, but can reach any complexity according to your requirements. But for a preliminary stage, it's probably sufficient. So what are we going to do? So right now, this rooftop equipment is floating in the air. So we are in need of the building. So when carrying out a wind simulation, you have most of the time part of the structure that is of interest. In my case, it's the ventilation system, and I'm not interested into the building. So I could now, of course, model the building as well as a hull, for example, but I chose a different approach. So I prepared an IFC file. This I'm going to import, and this IFC file will be a so-called surrounding object. So this will be part of the wind simulation, but it will not be part of our static analysis and everything in the design process later on. So I can just import this IFC file, and lately there have been some changes to the settings. So formerly, if you went to calculate the mesh settings and you had the wind simulation add-on activated, you got this new tab, and here were the settings for our shrink wrapping. So what is shrink wrapping? Maybe a quick recap, because it's very important to understand this. So shrink wrapping is not actually a part of CFD. It's a functionality that is one of the main advantages of our wind. So if you carry out a CFD analysis with any CFD program, you need a structure that is, topologically perfect. What do I mean by that? So right now we're looking at a static analysis model. Just quickly going to just hide this. So, and it's perfect. These are the middle surfaces here of the structure of these sheets. But in reality, or let's say in the background, we actually have something looking like this. So I have to zoom in a little bit here. Wait. Maybe make them a little bit. So here. So these sheets actually have a thickness, and we can display them as extruded thickness, but that also means that this is not how it looks in reality, right? So what we have now, we have, let's say, volume elements that intersect with one another. So we don't have a closed hull, and this is a requirement when carrying out CFD analysis. So what can we do? So what you usually have to do is you have to run or you have to prepare your model for the calculation. So you have to fix your geometry, you have to patch all these openings, and you have to clean up all the intersections and so on. And this is quite amount of work. And if we have RFM 6 as a starting point, we don't want to do this. We want to start with a static analysis model. So what we introduced is a so-called shrink wrapping. So it is basically what it says. So it's we are shrink wrapping a geometry. So we are putting a polygon mesh above this structure, and we can decide how fine or coarse this polygon mesh is. And this wraps around the structure and generates automatically a closed hull, and hence produces a calculatable CFD model. So back to the shrink wrapping settings. So if we go back here, so formerly we had one shrink wrapping setting for everything, and now since a couple of months it is possible to assign these shrink wrapping settings to every object individually. So there's still a global setting that you also can adjust as before, but you can create new shrink wrapping settings and assign them to specific objects. So if you have a specific area that you want to have a finer mesh on, you can do this. All right. Also, you can apply different shrink wrapping settings to the surrounding objects and the main structure. So the main structure is what we are going to calculate, our ventilation system, and the surrounding object is, in my case, the building, but anything that you import as a IFC file or STL file or something like that. Good. Maybe back to the IFC file. So if I want to apply such a shrink wrapping setting to a specific object, I can go to the object and activate this checkbox, specific wind simulation settings, and here I can pick another shrink wrapping setting that is different from the global setting, and then this specified shrink wrapping setting will be applied to this object. The same goes for roughness and permeability settings, which we are not going to use today, but they also are defined on or can be defined now on an object basis. It is also possible to exclude a certain object from the wind tunnel with this setting. So if you want to, not delete any object, but just temporarily exclude it from the wind tunnel, you can do this here. So now to the IFC file. So if I go to the IFC file and I also want to make changes to this specific file, I can go here to the Edit IFC model. And here I also find this checkbox. So here I can apply the same settings as for the real objects that I have in RFM6. So this is the shrink wrapping mesh, but with a CFD analysis, we have more than one mesh. So we have the shrink wrapping, which is the simplification of the structure. Then we have the volumetric mesh. So if we create here a load case using, for example, our load wizard, and here, all right. And now we have this wind tunnel, and this wind tunnel is a 3D box. And yeah, in this box, there's air. And this air has to be meshed to be so we are able to carry out the wind simulation analysis. That means that we have this volumetric mesh that fills out the box. And this, the algorithm that creates that mesh, now interacts not with the original geometry, but with the shrink wrapping mesh, if it is applied. So if I have a perfect geometry, like my building here, it's an IFC file, but it is completely closed and, let's say, ready to calculate structure, there no shrink wrapping is needed, and hence it will not be created for these objects. So if I have a perfect geometry with my static analysis model, for example, if I have one simple plate or sheet, let's say, it's a perfect box. So there's also no shrink wrapping needed. But if there are intersections or anything's not like CFD calculation ready, the shrink wrapping is applied. So now we have this volumetric mesh generator, and it now tries to snap to this shrink wrapping. We are going to look at it later, how that looks like. And it is important to understand that the shrink wrapping mesh and this volumetric inside, let's say, that is closest to the model, they are not the same. So the this inside of the that is closest to the structure, we are going to call computational mesh. That is what we are going to see later in the results as an option. So, and here is something important to know. So since we have the original model and we have the shrink wrapping hull, let's say, there's a gap between them, and we have to transfer the loads that are calculated to the original model. So there's a small error during this transformation process. And to minimize that error, it is important that the calculation mesh, so the volumetric mesh, has a smaller density or equal density than the shrink wrapping mesh. So if the shrink wrapping is finer than the volumetric mesh, the error increases and gets like too high, or let's say it's not sufficiently accurate anymore. Okay, maybe one other change before we are going to look at the meshes. So formerly, it was possible also in the settings of in the mesh settings to choose an IFC terrain. This option now has also moved. So now you find it on the base data terrain, where you also found in the past the simple planes, but now here you find the option for the IFC terrain if you want to use one. In my case, I don't want to use it. So maybe let's take a look at these different meshes. So if I go to calculate, I can go here to rwind and select a load case. Why do I have to select a load case? In RFM6, we have multiple load cases in one model file, but with the CFD analysis, it's always one load case is one model file. Why is that? So for one analysis, you have one wind tunnel with a specific size, and we have one model file that is rotated it in the specified angle, and this cannot be done in the same file with rwin3. So here you select the, let's say, rotation of the model, and then the geometry is exported and made ready for the transfer. rwin3 is started up and on the wrong monitor. I need a license. And now the objects are placed, and what you just saw is automatic resizing of the wind tunnel. So and this is another advantage of rwind. So usually the size of the wind tunnel has to be determined by the user. This can also be done with rwind, but we also have implemented a automatic algorithm that takes into account various parameters, as for example the size of the model, and has some default size, which is a compromise between accuracy of the results and the calculation speed. But if you want to adjust the wind tunnel size, you can do so at any time. So if we are in rwind, we can here check this show simplified model checkbox. And now, in the small scale, something happened. So if I check this off, we see the geometry that has been transferred from RFM6, and now you can see this shrink wrapping mesh. The resolution of this mesh can be set. So in RFM, we saw it already. If we are in rwind, this can be found under models here. So we have this level of detail parameter. So the higher the level of detail, the finer the mesh. And what does this level of detail mean? So the algorithm that generates the volume mesh works like you have a certain basic mesh size, and this basic mesh size gets like the distances are halved. So if for example I start with 1 meter, then the level of detail 0 would be okay, I keep my 1 meter. And if I have a level of 1, I have 50 centimeters, and level 2 is 25 centimeters, and so on. So that's why, or like how this is working. But depending on what you choose, you also get a calculation of how, like what result you get. If you pick the detail size, on the other hand, you can specify a certain value, but what that does is it's just looking for the most adequate level of detail instead. Now on to creating the mesh, the volumetric mesh. So here I'm going to simulation, generate mesh, and this takes a little bit longer because in CFD we're usually talking about a number like 6-digit number of cells, of elements, so up to 7 or 8-digit numbers. So it's a lot. You have a lot more finite elements than with a static analysis. That's why the calculation times are also longer than we know that from a finite element analysis. And in our Win3, we use this snappy hex mesh algorithm that is part of the OpenFOAM solver, which is the basis of the calculation. And it basically works like this. So you have this wind tunnel box, and it is filled with regular boxes, like mesh elements. And then the mesh is refined around the model, and then the elements that are inside of the model, where there is no air that is calculated in CFD, they are deleted. So this is like a multi-phase algorithm, and that's why right now you saw there were 700,000 or so, and then the number dropped again, because then the elements are deleted that are not used in the calculation. So should be ready in a bit. Here on the left, you can, by the way, see the different models. So each shrink wrapping setting from RFM6 is like one model file. So here you can see that our main model has a shrink wrapping setting, and our other model, there is no shrink wrapping applied because my building model is ready to calculate geometry. Maybe one more thing that we also can see here. So usually when you carry out CFD analysis, you have to refine the mesh around the structure you want to analyze. This is something you, with other programs, have to do manually. In our Win3, you can do it manually, but by default, there's also an algorithm that we implemented that automatically refines the mesh around the model. So you can see here on the floor of the wind tunnel on the bottom that there are finer element sizes near the model, and it depends on the settings how many of these mesh refinements are stacked on top around the structure, and how fine the refinements are. So here you can see that. So on the outside you have the big elements, and the elements are getting finer the closer we get to geometry. And now we can also take a look at the mesh sizes. So here we have on the left and top like a section through the volumetric mesh. We can also see our boundary layers, where we have additional refinements around the structure. And here we can see the shrink wrapping here in blue, and you can see that they almost match, but not exactly. So that's what we have to take into account. So here the mesh sizes are somewhat equal, so I think it's okay. So these are the default settings. So if you go with the default settings, you should be okay. But if you plan to refine your shrink wrapping settings to get a closer representation of your structure, please have a look at the volumetric mesh so it is not coarser than the shrink wrapping mesh. Okay, so let's go back to RFM6 and take a look at this mesh refinement factor that I was talking about a while ago. And these can be found in the wind simulation analysis settings. So here you have this finite volume and density factor. And the higher the number, the higher the number of elements will be, and also the mesh refinement, the number of mesh refinements changes, and the mesh size also changes. Please note that this factor is not, or this algorithm doesn't behave in a linear way. So if you want to carry out a mesh independency study, this can hardly be done by using this algorithm, let's say. Here it is better to use manual mesh refinements, because it's an algorithm that is doesn't refine the mesh linearly, and hence it is not suitable for a mesh independency study. Okay, then we can take a look at the analysis settings more closely. Today I want to talk about three different parameters. So one parameter is the finite volume mesh density. So for my variance study, I tried two different mesh densities, and also I tried two different turbulence models. So by default, the runs K epsilon turbulence model is activated. It has its strength in simulating the free flow. So when we are in the air and there's no structure blocking the wind flow. And then we have the K omega turbulence model, which has its advantages if we talk about the boundary near calculation of wind, so around walls and so on. And the K omega SST turbulence model tries to combine the best of the two worlds. So we have the K omega simulation or turbulence model in the area around the structure we want to calculate, and the free flow is calculated with the K epsilon turbulence model. And between these two models, there's some intermediate algorithm that tries to bring the two together. And the third thing I want to point out today is the number of iterations. So this is a concept we already know from finite element analysis as well. So by default, RFM6 stops the calculation of load case after 100 iterations to avoid indefinite calculation if there's a calculation that cannot converge. By default, we have a maximum number of iterations of 500, but here I also experimented with a higher number of iterations. So these are the settings I adjusted during the study. Then we can go on to the results. So for the results, I want to first point out here an online manual of ours. So CFD is a quite complex area, and it's not easy to understand or to validate. So if I have a single span beam, I have some analytical formula that I can check if some program calculates the forces correctly and so on. But for CFD analysis, there is no analytical formula that you can take. Well, okay, so there are some for simple geometries, but for the more complex application, it's not as easy possible. Of course, you can have some testing data, but these have to come from somewhere. And to get some idea how it works, what things are important, we created this CFD analysis application online manual. You can find it under resources, online manuals, and if you filter for R13, you have the R13 online manual, of course, but also you can find this CFD analysis application manual, where you find some interesting information, and it gets you started with the topic of CFD analysis. Then again, we have a lot of content. We have knowledge base articles, verification as examples, and so on our website. Feel free to explore and learn about CFD. Then I have prepared the result model files because the modeling takes, or the calculation takes quite a while. So first, I want to show you a model where I had a look at multiple directions. So I made a full 360-degree calculation with a step size of 22.5 degrees. And this is also a new feature that came into the program recently. So here we have our results for this load case number 2, and I calculated multiple load cases here, turning the wind tunnel about the building like this. And here we have, of course, the static analysis results, but for these wind simulation load cases, we also have the wind simulation analysis results. And here I can show you now the result types. So we have this computational model. So the computational mesh is quite similar to the shrink wrapping mesh, as I said before, but it's not the same. So it's like the out or the inside of this volumetric mesh where the calculation is performed. So this is the computational mesh, and then we have the original model, which is our RFEM geometry, and there we have this interpolator that transfers the load from the computational mesh to the original model. Now we can look at different quantities. We can look at the pressures. We can look at flow field quantities like the wind speed about our building. Maybe choose a different one. Okay, here. And also came recently into the program are the streamlines. So streamlines is something that was already possible in RFEM 3. Now we can have a basic view of the streamlines in RFEM 6. Right now we're working on bringing more options to control the number of streamlines and their position in RFEM 6. If you want to take a look at the streamlines in a more comprehensive way, feel free to go to our wind and use the full feature streamlines there for the moment. Now, I have these results, and maybe I'm interested in combining these results and having an envelope of them. And this is possible since a while. So if you create a result combination, by default, this tab is not visible. So if you are missing it, go to Base and activate here the checkbox for the result combinations. If you generate one and you assign solely wind simulation load cases, you have another option here. So if I go to the result combination, usually you have the result combination for the static analysis, but we enhance the feature to provide also surface quantities for the pressure and the CP values. So here you have no option to display the results on the computational model. Why is that? So as I said, every load case, every wind direction has its own RWind 3 file. It's a separate calculation with a separate rotation of the model, with a separate shrink wrapping, a separate volumetric mesh, and hence all the meshes, the computation meshes, are not the same. So that's why we have to find the next common ground, and the next common ground is the original model. So that's why you can find the results for the result cases only on the original model file. But here you have the possibility to look at the minimum and maximum values calculated for each finite element separately. The next file I prepared is now about the 1 meter attic. Here I only calculated one wind direction, but of course this can be extended to do the full scope of the analysis. Here I only want to take a look at the differences. To make it more easy, I'm going to close the other files. And open the one with a 1.5 meter attic. And then we can take a look at the results side by side. So if I go to Window, tile vertically, I can. Oh, sorry, I opened the wrong one. This one. So you can see it here. I analyzed 3 different variants of the settings. So the first settings are the R-Wind and RFEM default settings. Then I applied a refinement regarding the number of iterations and also the refinement of the volumetric mesh density. And then I also changed the K omega to the K omega turbulence modeling, turbulence model. So now let's take a look at the results. So here I have no results. So I have to open the German version. They have results. Sorry for this interruption. So if the question comes up, how long did the calculations, how much time did it take? So depending on the load case and the settings, for this model, we had a calculation time of something between 5 and 25 minutes per load case. This highly depends on your machine, on the settings, but yeah. So for load cases, it's about 1 hour, let's say, because I had the different settings. So here the 1 meter and 1.5. So if we now place them side by side, so we have the 1.5 on the left and 1.0 on the right. Just going to hide the IC model to have a better view. So if we look at the 1.5 meter attic in the wind simulation results with the default settings. Here we can see we are going to compare the drag forces for this example. So here we have a drag force in the x direction of minus about 0.5 kilonewtons, whereas with 1 meter attic we have minus 0.1. So there's a difference. Then maybe let's take a look at. Sorry, this was the wrong comparison. I have to look at the load case 2. So here we have 1.2 kilonewtons in the positive directions. Here we have minus 1.5 in the negative direction. If we refine the mesh of the volume, we can see that here on the left the value changes to the positive, but slightly positive. Whereas here with the 1 meter attic, the drag force increases. And then if we compare it to the other turbulence model, we have 0.3 here and 0.1 on the right side. So as you can see, these are quite huge differences, not only compared to the sign of the value, but also its amount. And this is one of the key takeaways when dealing with a CFD. So CFD somehow works out of the box, but depending on the model, depending on your settings, depending on the wind speed and all the parameters that can influence CFD analysis, the results can change. And there is no globally best practice, like what settings you have to pick, but rather you have to try out different settings and see their effects. There's also literature about this. You can find content about it on our website. But in the end, this is something that comes with CFD analysis. So it's our wind and CFD in general is a great tool to analyze the phenomenon wind, but you have to get a feeling for it. You have to try out different settings and get to know the technology CFD to be able to apply it so that you can rely on the results. I hope that this webinar taught you something where you can now better understand how you can work with our Win3 and RFM6 in conjunction, which settings are important, and how you generally can carry out such a CFD analysis. If you have any further questions, I hope you asked them already in the chat. If there are any coming up in the future, please feel free to reach out to us via email or in our Dlubal community. And I wish you a pleasant day until the next time. Bye. And of course, I will give it back to Andreas.
Thank you, Clemens, for your presentation. At the end of the webinar, I have additional hints for you. For example, to our online courses, there's the RFM6 course. That's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design with RFM6. The Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design. And the Eurocode 8 course for the earthquake design. For more information, just scan the QR codes here or press the links. You can get such a course for free when you submit your customer project. Just scan the QR code or click at the link. Then there's a table where you can upload your files. You can also write me an email to info@dlubal.com to my hands, Mr. Herold, and I will write you back what files I need. It's not much work for you. And the courses are valued at 199 euros to 399 euros. Also a hint to our free online services, for example, the Dlubal community. You can ask questions to our software there. And we or other users will answer you. Then there's the GeoZone tool for the determination of wind, snow, and earthquake loads. The cross-section properties. You can download 3D models for free. For example, as a template for your project. You can download the free trial versions of RFEM, RSTAB, RSection, and RWind when you don't already use our software. Just scan the QR code. And you can explore all our free services when you click at the link here or scan the QR code. More information can you find on our website, dlubal.com. For example, the recorded webinars, the knowledge base articles. You can ask our AI assistant Mia all the time. And she will answer you. Okay, that should be also all from my side. I thank you for your attention. Thanks to Clemens for the presentation. I wish you all a nice rest of the day. I hope we meet each other in a future webinar. See you. Bye-bye.